So the goal is to see if the number of ER visits among male athletes is different from that of females. And we have the count type data. We've asked athletes how many times they've been to the ER. One person said 3 times, one once, and so forth. And we want to know if there are differences. From the looks of it, well, perhaps there are differences in the count. We don't know. So we define the difference delta to be equal to y minus x. As far as this problem is concerned, whether we have it as x minus y or y minus x really doesn't make a difference, because we're trying to see if they are different. We're not asking if x is going to be bigger than y or vice versa. So an appropriate test would be a two-tailed test. We have to find the rank sum statistic. So in order to do that, we have to put the data in order first, combined sample. So 0, 1, 1, 2, 3, 4, 4, 5, 6, 7. Good.
Did you change one of the numbers to 3 what you do?
I changed. Yes.
That's what
Did I?
At first you had 2 zeros on there.
I think I had 2 zeros here and then I quickly changed. Yes. So I can write. Got to get my other colors today. So 0 x. Does it matter which one I call as y or x? No. Now you may say, well, would it not affect the rank or the statistic? Do you think it would affect the statistic?
They'll have the same rank.
They will have the same rank. So if these were to be different, sure, the rank sum is going to change, but in this case, the ranks will be the same, so it really doesn't matter. So same traces like the previous test. When we have ranks, we take the average of the ranks and assign them to the observations. So if these 2 observations were different, I would have assigned 2 and 3. But since they are identical, I'm going to assign the average of 2 and 3, which is 1.5. Having assigned 3 ranks, what should the next rank be? Should it be 3 or 4? Jimmy? 4. So 4, 5. If these 2 observations were different, yes.
Average of 2 and 3 is.
Yeah.
Thank you. 2.5. So if these 2 were to be different ranks, I would have assigned 6 and 7. But since they are the same, I'm going to take the average of 6 and 7, which is 6.5. And I have assigned 7 ranks already, so the next rank has to be 8. So 8, 9, and 10. Good. So based on the convention that we had, based on the procedure that we went over, we defined the sample size of X to be M. In this case, it really doesn't matter. M is 5, N is 5. And based on the concept of our procedure, we simply added the ranks corresponding to the Y weights, Y observations. So and those are the ranks that we've got to add: 6.5 plus 2.5, 9, 9, 13, 21, 30. Yes, am I missing something? It's like that's 1 to me. So 2.5 plus 4 plus 6.5 plus 8 plus 10. That is actually a good observation by Chris. So if this were to be a sine rank test, a 0 would mean it's a paired data, there is no effect because of treatment. But the underlying meaning here is something else. We're looking at 2 independent samples, and one person says, well, I've been to the gym a lot, but I'm an athlete, but I've never been to the ER. So that is not the same as saying whether a treatment had an effect or not. So in this case, a 0 actually matters to us. So W is 31, but we have to find U in order to use the critical value from the table or using R. We know W is equal to U plus N times N plus 1 over 2. Five times 5 plus 1 over 2, 15. So U would be equal to 31 minus 15, which is 60. Yes. We also know U prime is simply U minus MN, so 16 minus 25, negative 9, but we know we cannot have a negative, so we keep it as positive 9. We would like to find the critical value on the left and the right to determine where the test statistics fall. In this case, we have 2 of them, one 16, the other is 9. So we use Q Wilcox. So we've got 2 possibilities. We always enter the area below. Alpha is 0.05. So, excuse me, 0.01. If alpha is 0.01, what is alpha over 2? 0.0. 0.005. We don't have to find both critical values. We find one, we can naturally find the other by subtracting it from m times n. So m in our case is 5, n 5, enter, I get 1. Good. On the other side, since that is 1, m times n is 25. 25 minus 1, we will have 24. Another way of doing it, change that to 1 minus 0.005, area below the right critical value, I get 20. Really doesn't matter. So 1 is over here, 24 over there. Where does the critical value lie? Does it lie in the rejection region? Excuse me, where does the test statistic lie? So 9 perhaps somewhere over there. That's u prime. U is 16. So they lie within those two limits. So we should not be rejecting the norm. There's, yes,
So U prime is the only one we're testing for?
come again.
The U prime, is that the only one we're testing with?
That's good enough, I just put in u. So in this case, it really doesn't matter whether you use u prime or u, right? Because one, you're doing two-tailed. If u prime rejects the null or doesn't reject the null, the conclusion would be exactly the same with u. They are symmetrical. So whatever happens on this side is going to happen on that side. So you don't have to test for both. One will imply the other. Good. I just put both in here because it's a two-tailed test. Now, this is a case, this is a large sample approximation. Excuse me, this is a rank sum test with ties. So when we get to the large sample approximation, the standard deviation will slightly change. The mean mu is not going to change, still mn divided by 2. And if you look at the variance, what was our variance from last time? So if you recall what we had last time, n times n plus 1 over 2. Yes. All we have to do is introduce a correction. I'll just call it, phi. That is a correction that we have to introduce in the variance due to times.
Professor,
Yes.
it's over 12.
Oh, thank you. 1 to G. So if we did not have any ties at all, we don't need that correction factor. That correction is required because we have ties. But the interesting part, though, is that this correction applies only to the statistic W, but not to U. So, well, if it applies only to W, and if you go back and look at the Wilcoxon sign round test, we took a similar approach. Well, we looked at the number of groups that were tied, the number of observations within each tied group. So here, how many ties we have? We have 2 tied groups. So T1, 2, T2, 2. 2 tied groups. Within each group, we have 2 observations. So what I have to do is take T1 equals 2, T2 equals 2, plug it in the variance for W. But keep in mind, mu that we used last time, it was for U or U prime. So mu right here, that formula is for U or U prime. For W, it was n times n plus 1 divided by 2. So here is the nice thing about Wilcoxon rank. Fine, there is an additional step. I have to do this correction. But do keep in mind, this applies only to W. Variance of U equals the variance of W. In other words, if I took the variance of this term on the right hand side, that phi wouldn't even matter to us. Do you agree? So if I take the variance of that correction term, it wouldn't matter to us when we use U or U prime. The only time that it would come into play is when we directly use the W statistic. Does that make sense? But if you go back and look at every single problem, we did not use the W statistic. We kept using the U or the U prime statistic. Does that make sense? So when we use the U or U prime statistic, we don't have to use the correction. So if you use W in your standardized test statistic, then that correction is required. Then we have to look at the number of groups that have ties and the number of observations in each of those groups. But if we don't use W, we'd rather rely on U, the mean of the statistic U. Or U prime, doesn't matter. What is the mean?
.5.
M times N divided by 2. You get 12.5. What is the formula for the variance? m times n multiplied by m plus n plus 1 over 2. What?
12.
Oh, 12, thank you. So 5 times 5, 11, 12. And just 3 points something. 23. 22. Which is approximately 23. So sigma squared is 23, which would simply mean sigma is the square root of 23. That's sigma, not sigma squared. Square root of 23, 4.8.
The other part, the variance, ties.
This one?
Is that it? With the variance ties.
No, this is required if we have to use W. But if we don't have to use W, then we don't have to worry about the ties. So 4.7.
958.
What is 4.8? So U is 16. The mean is 12.5 divided by 4.8. And what do we get? How much?
0.73 basically.
Approximately 0.73. What do we use to test? What distribution do we use to do a large sample approximation? Every single large sample approximation, what did we use?
Normal CDF.
Normal CDF, normal PDF, excuse me, inverse norm. Area is 0.005 under the curve corresponding to an alpha of 0.01. So if the area below is 0.005, how do we find that critical value? What function did we use? Inverse norm of the area below. -2.5, -2.5. This is -2.5. That will be positive 2.5. Where does the test statistic lie? The standardized test statistic. It lies right there. Had you used U prime, what would the standardized test statistic be? Take a guess. Instead of U, if you had used U prime, what would the standardized test statistic be? Negative 0.3. That's it. So that's why I said it really doesn't matter which one you use to test. So we all know how to find the p-value, but the exact p-value, if we want to find for a Wilcoxon-Rankin test, we need, since this is a two-tailed test, you've got to add the area above the test statistic and the area below the test statistic. In our case, you're not simply adding area above 16 and below 16. That would just be 1. So you have to add area above you to the area below you. U prime, I'm sorry. Good. And that gives us 0.48 for 1. Now, if you find the critical value using, p-value using normal CDF, you will find a similar answer. It'll probably be close to 0.6 or 0.3. You can use normal CDF, find the area above 0.73. But what should you do in this case? You have to multiply it by 2 because this is a two-tailed test. Good.